Hello everybody, my name is Roman Fajardo and the title of my presentation is Combinatorics Using Geometry. In combinatorics there are a few processes we can use to select sets. For example, the most well known, of course, is randomness. In this presentation, however, we'll be taking a different approach, a geometrical approach. We want to figure out a way of how we can organize players into two teams in a fair way where each player plays the same amount of games with each of the other players, where x equals the amount of players and x minus 1 equals the amount of games. First example we're going to go over is where x equals 8 players, and I have a project proposal where x equals 16 players. Some definitions before we get started. Galois field. Galois field is a basic field that contains a finite number of elements. During my presentation we're going to be working with Galois field 2, in which we get an ordered pair of 0 and 1. We're also going to be working with hypercubes. Hypercube is just essentially a 4-dimensional cube. For our first example, where x equals 8 players, we need to know that there are going to be 7 games between two teams, with each team consisting of 4 members. Our approach to solve this problem is to view the 8 players in pairs instead of groups of 4. This makes it a bit easier to visualize. And this way we can assign each pair of players to the same team exactly 3 times. Next, we are going to assign each of the players to a vertex of a cube as we see in figure 1. We also need to identify a key player so we can base all of work on, which would be corner 1 in figure 1. Knowing this, we're going to be working in Galois field 2 cubed. Since we're going to be working in a 3-dimensional space, there's a linear equation that needs to be satisfied, which is ax plus by plus cc equals d, where a, b, c, and d are all real numbers with the exception of 0. The same equation can be applied to Galois field 2 cubed, with the only difference being that a, b, c, and d are all elements of Galois field 2, which is 0 and 1. Next, we need to break up the cube in 3 parallel ways, which we get a vertical, horizontal, and right down the middle as we see in figure 2a, b, and c. Or we can also use the following equation, which is 1x plus 0y plus 0c equals 1, where 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1 are all, as we see, these points are the red points in figure 2a. For figure 2b, we can use the following equation, which is 0x plus 1y plus 0c equals 1, and for the final figure 2c, we can use the equation 0x plus 0y plus 1c equals 1. Knowing this, we know that the finite geometry of Galois field 2 cubed has 14 planes that go through the point 0, 0, 0, meaning that there are 14 ways of choosing A, B, C. The equations that correlate to this are x equals 0, y equals 0, z equals 0, x plus y equals 0, x plus z equals 0, y plus z equals 0, and x plus y plus z equals 0. The other 7 planes would be the same, with the only difference being that instead of equaling 0, they would equal 1. Now, to get the last 4 figures, we're going to use the following expressions, which are x plus y, x plus z, y plus z, and x plus y plus z. With if they are equal to 0, they are red points, and if they are equal to green, they are green. If they're equal to 1, they are green points. And here are our results. The following table is our results from the previous 2 figures, figure 2 and figure 3. As we can see, each pair of players is on the same team exactly 3 times. For example, if we were to take the pair 1, 2, we can see they are the same red team 3 times during game 1, game 2, and game 4. Now, for my research proposal, we would take a similar approach, but instead of working with 8 players, we're going to be working with 16 players. Like the first example, we're going to be working with Galileo's field. Unlike the first example though, we're going to be working with Galileo's field 2 to the 4th power, meaning we're going to be working in a 4-dimensional space. There is also a linear equation that needs to be satisfied in a 4-dimensional space, which is ax plus by plus cc plus dw equals e, where a, b, c, d, and e are real numbers except 0. This equation can be applied to Galileo's field 2 raised to the 4th power, with the only difference being that a, b, c, d, and e are elements of Galileo's field 0 and 1. After this, we're going to assign each of the players to a vertex of the hypercube, as we see in figure 4. Next, we are going to break up the hypercube into parallel ways as we did it in the previous example where x equals 8 players. But instead of getting 3 parallel ways, we're going to have 4 parallel ways as we see in figure 5, with 5a being a horizontal way, 5b vertical way, and 5c and d being in a diagonal way. Knowing this, we know that in GCF, Galilean field 2 raised to the 4th power has 30 planes that go through the point 0, 0, 0, 0, meaning there are 30 ways of choosing A, B, C, D, and E. The equations that would correlate to this would be x equals 0, y equals 0, z equals 0, w equals 0, and so on. The other 15 planes would be x equals 1, y equals 1, z equals 1, w equals 1, and so on. In order to get the last 11 figures, we would use the following expressions: x plus y equals z, x plus y, x plus z, x plus w, and so on. In conclusion, and some further research. In conclusion, even though it hasn't been proven yet, it is believed that this process works for a larger number of players that are divisible by 4, with the exception of 12. 12 is a special case. In other words, any number bigger than 16 that is divisible by 4, this process is said to work. Some applications to this would be sporting events such as track and field. If we just have n x number of players and x sporting events, this equation can be applied. And here are my references. And any questions? Thank you.